Hi. So we go and describe this other chapter, chapter 9, which is velocity profile for circular sections. And the reason I used to call it velocity average velocity is to which we need to consider in calculating Reynolds number. I will explain that in the following presentation. So the contents, we introduce the concept, velocity profiles, which explain to us why, how it looks like for laminar flow, how this profile looks for turbulent flow. And we've seen that in the applied computational modeling when you do the CFD analysis for this type of applications. And let's define the concepts in a way that explains to us what we're trying to achieve. So if you take a cross section of a circular pipe through which a fluid, for example, water passing through it, flowing through it, you'll find the velocity of the fluid flow differs from point to point in the cross-section area. So the flow particles at the surface area of the circular pipe, there would be zero, and if it's in the middle, would be slightly different at the center line of the pipe, and therefore we want to explore that. The velocity at the pipe wall, which I say is zero, as the fluid is in contact with the stationary pipe. As you move away from the wall, the velocity increases. Where do you think will be the maximum velocity of the flow? Which I just answered that. So usually it will be at the center line of the pipe because the pipe is a circular, so that's where it should be. One application of this is heat transfer from hot water pipes in your home. When hot water flows along the copper pipe, the amount of heat transferred from the water to the pipe wall to the surrounding air depends in part on the velocity of the water in the thin layer, the boundary layers closest to the pipe wall. The way in which the velocity differs along the cross-section of pipe depends on the nature of the water flow. And from the textbook, we are in chapter 9, you can see the following images for laminar flow regime and turbulent flow regime. The image below shows the general shape of the velocity profile for both laminar and turbulent. The velocity at the pipe wall is zero. That's where you can see it at those points, zero. And here in the center line of the cross section of the pipe, which will be the maximum. However, in turbulent, it's not easy to find where is the maximum because everything is disturbed. So for laminar flow, the velocity increases until it reaches to the maximum of the center line of the pipe. The parabolic shape of the velocity profile comes from the nature of the laminar flow, which may be thought of as a series of concentric layers of the fluids sliding along each other. However, for the turbulent flow, we recall there was a significant intermixing of the particles and the consequent transfer of momentum between them. This gives rise to more uniform velocity across the cross-section. Therefore, the velocity at the wall is also zero. The local velocity increases rapidly over a short distance from the wall. So you don't get that nice shape parabolic. So you get the shape like that because it's close to the wall, start increasing slightly till goes to a velocity. Therefore, the one we assume for both, it should be the average velocity, not the maximum, not the minimum, which is zero, is the average. So whatever is the maximum for the laminar divided by 2 will give you the average velocity. Here is slightly different. There are special equations to do that. Because of the regularity of the velocity profile in laminar flow, we can define an equation for local velocity at any point within the flow path. So if we call the velocity u and the radius is r, the maximum radius is r naught, and the average velocity v, then u equals 2v1 minus r over r naught square. Example. An example problem 1 from the previous lecture, so 18.1 in the previous video from the textbook. We found that Reynolds number is about 6,708 lamina, which represent laminar flow for the glycerine at 25 degrees Celsius flow with an average flow velocity 3.6 meters per second in a pipe, having a 150 millimeter inside diameter. Thus the flow is laminar. We try now to calculate on the velocity profile from the pipe wall to center line of the pipe in increments of 15 millimeters. Plot the data for the local velocity u versus the radius r. Also show the average velocity on the plot. So these type of questions, you can come with this following. R naught is equal to the diameter divided by 2, because R naught represent the radius, or the maximum radius in this case. 150 divided by 2 is 75. At R equals 75 millimeters, R naught at the pipe wall, R over R, so that ratio is 1. So U will be equals to 0. This is consistent with the observation that the velocity of a fluid at a solid boundary is equal to the velocity of the boundary. When R is equals 60 millimeter, U equals to 3.6, and then you have the ratio, which is represent for us 60 divided by 75, which is the R naught, and that will give us 2.59 meters per second. We can see this is in table, so to go through that equation, it's better to see it in that shape. So you have R naught 0.707 R is equals 0.707 R naught from here to center to that point. And here we say the U maximum is about 2 average velocity, because it's the average velocity equal the maximum divided by 2. And here you could find where is exactly is the average velocity is 3.6 meters per second. That's what was given to us in the question here. But to find that, if we do from 0 radius to go to the 75, the full radius, you find the ratio between the R and R naught. What's the R naught? Is the 75. So 75 divided by 75 is 1. 60 divided by 75 is 0.8. 60 is 45 divided by 75 is 0.6. Still 0 divided by any number is 0. And then based on that, you calculate the U based on the equation we just defined here, the 2 times the velocity and that ratio. You will get the velocity at the wall. So here we're moving from 0 to the radius 75. At the wall, when it's 75, here the radius is 0. But when you go to the middle, you get the maximum velocity, which is 7.2. So that 3.6 times the 2 will give you the middle of the pipe, which is the maximum velocity going through it. That's when it's at the center, and which is the average of it. So technically, in the questions we've seen in fluid mechanics, these here, it's always should be considered or notified to you. This is the average flow velocity of 3.6 meters per second. So we're not taking the maximum, we're not taking the minimum at the ball, we're taking the average, that line of it. Now, for laminar flows, it's easy to see that. For turbulent flow, it's slightly different. So the velocity profile for turbulent flow is very different from the parabolic distribution for laminar flow. The fluid velocity near the wall of the pipe changed rapidly from 0 at the wall to a nearly uniform distribution through all the bulk of the cross section. The actual shape of the velocity profile varies with the friction factor F, as you remember, when we calculated from Reynolds Moody chart, and based on Reynolds number relative roughness, intense varies with the Reynolds number and the relative roughness of the pipe. The governing equation for that required this friction factor. So it would be V 1 plus 1.43 to the square roots F plus 2.15 F log 10 1 minus R over R1 R naught for it. And then you can perform the same calculations for it. You can see if I want to find the maximum here, U maximum for turbulent, don't confuse yourself. It's showing here, this diagram is showing both laminar and turbulent, how they look like. So that is the laminar. We say the average would be here. It's maximum divided by 2. But the turbulent, you see it started from 0 at the total radius. But when it comes to a certain point, you can say this is possibly the maximum point, and the average for that one, it's here. It's slightly different from the average for the laminar flow. So to calculate that, alternate from this equation can be developed by defining the distance from the wall of the pipe. Y is equal R naught minus R. And then the argument of the logarithm term becomes 1 minus R over R naught. You rearrange this equation maximum velocity, v equals 1 plus 1.43 to the root square of f. The figure to the right compares the velocity profile for laminar flow and for the turbulent flow at the variety of the Reynolds number. This is, you don't need to really like, we're not solving questions related to determining the average velocity, but for you to understand, because I've seen this with many students, they think what we solve in Reynolds number is actually, it is the maximum velocity. It's actually not. What we're trying to solve is using the average velocity, which is given based on using these equations, or you're finding it based on the shape of the profile for it. And that's easy to see it with applied computation modeling when you do the CFD modeling, because you can see the software will to give you the maximum and average and minimum value for it. So that's all for us as a short about the velocity, so we can identify them and understand the difference between laminar and turbulent velocity. Thank you.